All right, so let's just jump right in. We've all heard the story, right? The one about how everything, well, began. You know the one, a massive Big Bang, this ever-expanding universe. It's a really neat, tidy story that takes us from a single tiny point to, well, everything we see today. But what if that story isn't quite as solid as we thought? What if it's starting to show some cracks?
I love this quote because it just perfectly captures what's happening in cosmology right now. It's this uneasy feeling. It's like we thought we knew the layout of the room, We had it all mapped out. But now, a few new measurements are making it feel like the very foundations, the floor beneath our feet, might be shifting.
And look, for decades, this standard story, our theory of everything, has been a huge success. I mean, it explains so much. It accounts for the background radiation of the universe, why galaxies are clustered the way they are. It's been an incredible tool. But recently, a few pieces of data have popped up that just, well, they don't fit. They don't belong in the picture we've painted. And that really is the question, isn't it? It's like finding a single loose thread on a beautiful, perfect sweater. You can either tuck it in and pretend it's not there, or you can give it a little tug. And what happens if you pull it? Does the whole thing start to unravel? Well, in this explainer, we're going to pull that thread. All right, Section 1, a crack in the cosmos. So our investigation starts with what sounds like a really simple question. How fast are we, our solar system, our galaxy, moving through space? You'd think that would have a pretty straightforward answer, right? Well, it turns out it really, really doesn't. Okay, so there are basically two main ways scientists try to answer this. On one hand, you've got the cosmic microwave background, or CMB. Think of it as the afterglow of the Big Bang. It's supposed to be the ultimate stationary background of the universe, the one true rest frame. Then, on the other hand, we have this massive survey of over 1 million quasars. These are super bright, super distant objects scattered all across the sky. So, two different rulers to measure the same thing. Now, here's where it gets crazy. Logically, these two measurements, they should give us the same answer, right? I mean, they're both supposed to be measuring our motion against the backdrop of the universe. But they don't. Not even close. They are wildly, fundamentally different. Just look at how different they are. The CMB measurement, they call it the CMB dipole, says we're cruising along at about 370 kilometers per second, headed toward the constellation Leo. Okay, fine. But the quasar survey? It clocks us at a speed that's 4 to 5 times faster. And get this, it says we're heading in a totally different direction, almost 90 degrees off. This isn't a small mistake or a rounding error. This is a flat-out contradiction. And this is the kicker. This isn't some statistical fluke, a weird blip in the data. The disagreement is measured at over 5 sigma. Now, for anyone who follows particle physics, you know that 5 sigma is the gold standard. It's the benchmark you have to hit to announce a major discovery, like the Higgs boson. It means the odds of this just being random chance are something like 1 in 3.5 million. So yeah, something is definitely wrong here. So if the measurements are giving us two completely different answers, maybe the problem isn't the act of measuring. Maybe the problem is with one of the rulers we're using. And that leads us to a really big question, which is our next section. What if we need to start questioning the cosmic echo itself? The cosmic microwave background. You know, it's worth remembering how we got this story in the first place. It all starts with a measurement, a hard fact. We detect this faint microwave glow coming from every direction in space at a temperature of 2.7 Kelvin. Okay, that's data. Step 2 is interpretation. We create a model that says, aha, this must be the leftover heat, the afterglow of the Big Bang. And from there, that interpretation becomes a narrative, a story we all know. We call it the baby picture of the universe. But here's the thing. What if that interpretation, that middle step, is wrong? Because that whole baby picture story, it rests on some pretty big assumptions. For example, it assumes the universe is isotropic, that it looks basically the same in every direction. But hey, that quasar data we just saw seems to disagree, right? It also assumes that when we see light from a distant galaxy that's been redshifted or stretched out, the only thing that could have caused that is the expansion of the universe. But is that really the only possibility? These aren't solid facts. They're the foundational pillars of a theory. And it looks like those pillars might have some cracks. Okay, so if the standard model is in a bit of trouble, what could a possible alternative look like? Well, it might involve a force that we tend to forget about when we're talking about the cosmos, even though it is quite literally everywhere. 99%. Just think about that number. What could that possibly be? It's not dark matter. It's not dark energy. It's something we can actually see and measure. It's the percentage of the visible universe that's made of plasma. Yeah, we have this image of space as this cold, empty vacuum, right? But it's not. 99% of it is this dynamic, electrically charged fluid. So what is plasma? Simply put, it's a gas that's so hot and energized that its electrons have been ripped away from the atoms. And here's the crucial part. Because it's full of these free-floating charged particles, it reacts really strongly to electricity and magnetism. This changes everything. It means the universe isn't some neutral, empty stage. It's more like a vast electromagnetic ocean. And that brings up a huge question. We've been assuming that redshift is only caused by the expansion of space. But what if light traveling for billions and billions of years through this electric ocean gets affected? Could the plasma itself stretch the light? Could it scatter it? Could it change it in ways our models just don't account for? All of a sudden, you have a totally new possible explanation for what we're seeing out there.
See? We're pulling that thread, and it's leading somewhere pretty radical. Because if the CMB isn't a baby picture of the universe, and if redshift isn't just about expansion, then what does that mean for the Big Bang itself? Maybe the whole origin story needs a rewrite.
Here's a really different way to think about it. What if the universe didn't start with a bang? What if instead it cohered? Instead of a single violent explosion from a single point, imagine a universe that's sort of crystallized, that pulled itself together out of a background of pure chaotic potential. Not an explosion, an emergence. So in this kind of model, you start with something called quantum foam, just pure, random, chaotic potential. But then, kind of like ice crystals forming on a window, little islands of coherence, of order, start to appear. These islands bump into each other, they merge, they grow, and they form stable, persistent chains. And those stable chains of cause and effect, that's what we call space and time. And the first light we see, it's not the afterglow of a bang. It's the light that finally appeared once the universe's structure became stable enough to support it. So we have this standard story on one side, and these really challenging, fascinating new ideas on the other. And that brings us to what I think is the most important takeaway from all of this. So after all that, after looking at the cracks in the standard model and exploring these wild new possibilities, what's the answer? What's the real story of how the universe began?
The answer is, I don't know. And honestly, that is the most scientific answer anyone can give you. The second you stop thinking of a model as a perfect photograph of reality and start seeing it for what it is, a temporary tool, a scaffold we're using to build our understanding, you realize just how much we don't know. And admitting that isn't a failure. It's the absolute starting point for any real discovery. And that really is the ultimate takeaway here. Mystery isn't some problem that we need to solve and get rid of. It's the baseline. It's the fundamental nature of existence. It's the engine that drives science forward, that pushes us to ask bigger, better questions, to come up with wilder ideas. And it's a reminder that even our grandest stories of everything are really just our best guess, for now, in a universe that is way more mysterious and fascinating than we can probably ever imagine.